Welcome to Let's Learn Algorithms. In this series, we've been covering different types of algorithms and data structures, and not only how they work and how you might go about visualizing them, but we're also trying to cover how you would implement them in your code and working through real-world problems that show this in action. So in this series of videos, we're going to talk about graph theory, which is essentially the study of graphs. So that leads us pretty much straight into the question of what is a graph? So to answer that, I'm going to first just show you a graph, and I'm going to start to talk about the components of a graph so that you can understand what I'm talking about as we proceed through these videos, and you really understand the pieces of it. And then after I show you, the names of these different pieces and sort of talk about them, I'm going to show you an actual real-world example of how you might map data to a graph. So in this case, we've got a graph with random numbers, and we're going to start with the blue part, which is called a vertex. A vertex is sometimes called a node or a point or a data point. It's essentially just something that represents a stage, a process, a piece of data, something like that in your graph. So you'll see this one. We've got the one colored in blue, but all of these circles are vertexes, and they represent different data points. In this case, they're just numbers. The next thing that you'll want to look at is the red line, which is an edge. So you'll also hear these called an arc or a line, and edges are going to represent relationships between different pieces of data or different stages. Basically, they're representing relationships between vertices. So an edge is any of these black lines you're seeing, including the red one. They represent some sort of relationship between these two items. And oftentimes what they'll mean is that you can maybe transition from one data point to another, or maybe you can use this 2 to generate a 4. Then you can use the 4 to generate an 8. So this graph isn't really clear what the lines mean, but the edges are, they're going to mean that there's some relationship between them, that it means that something important is there. So this will all make a lot more sense if we look at a real-world example. So I'm going to pull up this map from Google Maps, and I've intentionally zoomed in and gotten rid of, there's not many roads here. We've just got a couple roads and a couple cities, but we're going to show you how you might churn a map of cities and roads into a graph. The first thing that you'd want to do is to decide what your vertices are. So in this case, our vertices are going to be the cities. So each city is a point on our map that we might want to travel to. And we might want to calculate things like the minimum distance between two different cities, or the minimum distance you need to travel, or you might want to calculate the cost to travel from one city to another, both in terms of maybe tolls, or you might want to calculate it in terms of time taken to travel. So every city becomes a vertex, and then after you've created all the vertices, you would put the highways as edges between the two cities. So what these highways represent is a connection where you can drive from one city to another. So the relationship represented by these edges is, okay, you can drive from Dickinson to Bismarck, and that's why we have an edge there. So you'll notice that even though you can go a long way from Dickinson all the way to Rapid City, we don't actually make a connection between Dickinson and Rapid City right now. Right now we're just doing the most basic connections possible. So we do Dickinson to Bismarck, that's one direct connection. We go Bismarck to Fargo, and that's one piece of this relationship. So we aren't doing any other connections just yet. You could, and it wouldn't necessarily break your graph or anything like that. But for now, I find this to be the easiest way is to sort of, break it up as Bismarck is an actual, you don't have to stop there, but it is like a spot that you could go through to get to Fargo. Now, before we can sort of jump into the rest of these videos and talk about algorithms and stuff like that, it is important to look at the different pieces of data that might be associated with your edges, your vertices, and your graph. Now, the first part isn't necessarily something that is specific to an edge or a vertex, but it's just sort of an attribute of a graph in general, and that's whether or not the graph is cyclical or acyclical. Now, this doesn't always matter for what you're doing, but I think it's worth mentioning because a lot of these algorithms we'll be working with, the way you implement them and the way you actually use them will vary slightly depending on whether or not a graph is cyclical or not. So a cyclical graph means that you can leave one spot and get back to that same vertex, through a series of edges. Now, in this case, there's not really a good example of it. So let's imagine that this road from Fargo to Sioux Falls, you could drive from Fargo to Sioux Falls, and then you could get in your car, turn around, and drive back to Fargo. So that comes from the fact that this edge here doesn't have a direction. It says you can go either direction. You can go north or south on it. So technically this graph is cyclical. It is possible to go one way or the other. So whenever you're writing your algorithms, you might want to sort of take that into consideration is how does that affect what I can and can't do, or do I need to change my code to sort of prevent those cycles from happening? The next thing that I want to talk about is that edges can be directed, and I sort of alluded to this in the in the last example where I talked about Fargo and Sioux Falls. That is a bidirectional edge where you can go either direction, but sometimes you'll have edges where you can only go one direction. So from Sioux Falls to Sioux City, I'm going to pretend like this is a one-way road and you can only drive south. There's no way to drive back north on that road. So when you have directed edges, it's generally a way of saying that there's only data or cars or whatever can only go one direction. Another thing to keep in mind is that edges can sometimes have costs associated to them. So in this case, we've got a $5 toll going from Bismarck to Fargo. Now, the toll or the costs can be different depending on what situation you're in. Sometimes the costs will be time, sometimes they'll be money, and they might be something else entirely. But costs are just something that say that every time you send one unit of something, so in this case one car across that road, it's going to cost you this much. The last thing that we're going to look at are capacities, and I have this from Rapid City to Sioux Falls, and a capacity it's going to seem similar to a cost, but they're different in the sense that a cost is basically something that says you can send as much as you want across this edge, but there's a cost associated for every single unit. A capacity says you can only send this many things across this edge. So in this case, it might say you can only do 20 cars per minute, but it could also just be a constant number of this road only handles 20 cars and then it crumbles apart and breaks, and that road is no longer a valid road. So the capacity is going to be something that limits the number of things you can send across an edge. And where they'll sort of come into play in the real world is, well, in this example, it's not entirely realistic, but there is going to be some maximum number of lanes in a road. There's going to be some maximum speed limit. And you will have some maximum capacity of cars you can send through a road. If you've ever gone to LA during traffic hour, you've probably seen that there's definitely some maximum capacity of cars that can be sent down a highway.